Now, another thing for you to remember, we're always looking to simplify if at all possible. Now, that's very important when we come to differentiating. We don't want to have to differentiate something complicated if it's not necessary. We spend a lot of time learning how to simplify algebraic fractions. And one of the reasons why is because we don't want to have to differentiate a fraction if it's not necessary. There is a rule that you will learn later called the quotient rule that enables you to differentiate a fraction. However, students frequently get it wrong. Not because it's difficult, it's just because it could have, it's got a lot of negatives in it, and students can be careless. So, always consider whether a function you're being asked to simplify, or graphed for that matter, could be simplified. And if it can, then we will simplify it. Now, the biggest thing to be aware of is the fact that they're presenting you with a fraction. So it's not just any fraction also, and this is something you got to be aware of. It's a fraction where x appears both in the numerator and the denominator. We've had fractions previously. We've had fractions, but note on this one, for example, there's no x in the numerator. Likewise here, there was no x in the numerator. So these were very carefully chosen with no x in the numerator. Now, again, these have been carefully chosen to show you that it is possible that fraction can actually be simplified. And it says it would be best to simplify this function before differentiating. Now, we learnt back when we were doing algebraic fractions that in order to cancel down, you need to introduce multiplication of terms in your numerator in this case. There is only the one term in the denominator, so there's nothing we can do with it. But if we want to be able to cancel it, we can't cancel into expressions where there's addition signs. I'm wanting to create multiplication signs. Remember me stressing and emphasizing that the advantage of factorizing is it introduces multiplication sign between the terms. So if I can take my x cubed plus x squared plus x and factorize it, which I can. Remember, there is many different methods of factorizing as well. Common factor being the first one that we look at, and the first one you should always consider. Can I take out a common factor? And the answer is yes. And I've got an x squared plus an x plus a 1. Main advantage of all of this is there now is a multiplication sign between that term and this as a term. Bracket it, lock it together, and say that is a term. So that's what we do. So back to over here, I've factorized the numerator. Now I've set it up with the multiplication between this locked in term in the bracket and that x. So the x cancels, and really we have y is equal to x squared plus x plus 1. And to differentiate, do y with respect to x of x squared plus x plus 1 is very simple. It's nicely in a format where bring the 2 to the x, and remember I'm not needing to write dy dx because I am now actually carrying out the differentiating process which is bring the power to the front, subtract 1 from the power, plus 1. Do the same with the next term, do the same with the next term, and we get 2x plus 1. Now, that is much nicer. Well, at this stage, since you don't know the quotient rule, you wouldn't be able to actually differentiate that unless you had simplified it. And even when you do know the quotient rule, I'll be disappointed to see that you would jump in to something like this and attempt to use the quotient rule, because you're making the question more complicated. You're soaking up time. You're introducing opportunities to make silly mistakes with the quotient rule, especially considering this can be made so easy. I've written up the solution to this next one. It's very similar to the one I've just done. Let's stop and have a look at it though and break down this solution. So it says differentiate. Hopefully when you look at that, you see a fraction. You see more than a fraction. You see x in the numerator and x in the denominator. Now, why do I say you see more than a fraction? Because you've had fractions before and we didn't need to simplify them. And the reason we didn't need to simplify them was because x didn't appear in both the numerator and denominator. But now this is more fine detail that you need to be paying attention to. So we would like, and we can, simplify this algebraic fraction. You might look at 3x to the 4th minus 5x squared and say, well, why didn't you take out x squared? The reason I didn't, I could have, but the reason I didn't was because I only needed an x. I could tell that from the denominator. So I only took out x. And in fact, if you did take out x squared, then you actually will have a complication that, well, let me do it and show you why it's a complication. If I had said y is equal to x squared outside of 3x squared minus 5, which you can see is correct, all over x, then that and that cancel, still leaves an x outside, and I want now y dx of x outside of 3x squared minus 5. And I don't have a rule. I would call this a product. There is a multiplication in there. There's an x out here and there's an x in there, and I've got a multiplication. And I don't have a rule for multiplying. Not with differentiation, and not yet. However, we could get around it by saying, well, that is just the same as dy dx of, expand the bracket out, and you get back to your 3x cubed minus 5x, which is what you can actually see I've got there, because I only took the x out and I was left with 3x cubed minus 5x, differentiated that, bring the power, and it's nice, bring the power to the front, 3 3s are 9, subtract 1 from the power, minus 5. We would get the same answer eventually. 3 3s are 9, x squared minus 5. So while you get the same answer, you do set your question up, your solution up with a slight problem in it, because you've taken out more than you need. However, you can correct that so that you can just use our rule. And remember, at this stage, we don't have a rule for differentiating an x term multiplied, another name for that is product, times another little term, and once I bracket this, it's like I'm locking it together as a term with an x in it and an x out here. I don't have a rule for differentiating that. And with the example 2, you can see I've got an x squared in the denominator. So this time I am going to take out x squared. Taking out x squared is a possibility, leaves me with x squared minus 4. The x squareds cancel, so I'm going to differentiate x squared minus 4, which is simply just 2x. Could I please encourage you with example 3 to also pause the video? I'm going to pause the video. I strongly encourage you to, because have a look at what's happening here. Have a look at what's happening. I can't take x cubed out of the numerator. However, I need to move it out of the denominator. That's as much as I'll say. Please pause the video now and come have a go, because I'm going to pause the video and write out the solution. Okay, hope you've had a go at the solution. So what I did firstly was I broke this fraction up and wrote it as 1 over x cubed times the numerator. 1 over x cubed can be written as x to the minus 3 times this bracket. I don't want a bracket in it, but I know how to expand a bracket. It's x to the minus 3 times 1, and it's x to the minus 3 times 7x. So of course the first term, x to the minus 3 times 1, is x to the minus 3, and 7 times, we add the indices when we multiply, and minus 3 add 1 is minus 2. Now don't get that confused with what we do when we differentiate. We're multiplying terms, we add the indices. So if y is equal to x to the minus 3 plus 7x to the minus 2, we're now ready to differentiate. So we bring the minus 3 to the front, subtract 1, goes to minus 4. Bring the minus 2 to the front, and it goes to minus 14, x to minus 3. If you need to correct your solution, then do that. And we'll go back over any of these as many times as is needed for you to understand exactly what's going on. Make any notes and ask me about them, and you should be right to get started on 7D.